to this point in our discussion, we have been drawing Lewis structures for molecules without really stopping to consider what actual shape these molecules have. And it's time now to turn our attention to that question. The model that predicts the shape that molecules will assume is called the VSEPR theory. And in Chem 2A, this information is found in section 6.8 of your text. In Chem 22, it's found in section 10.7. Please note that in each of these sections, there is a very important table that you're going to have to commit to memory, summarizing the information that we're talking about here. That table is table 6.17 on page 204 in the Chem 2A text, and it's table 10.1, page 338 in the Chem 22 text. So let's explore what the VSEPR theory is proposing. Notice that this set of letters is an acronym, each letter standing for a word: valence shell electron pair repulsion theory, or VSEPR theory. And the name is very descriptive of what the actual model is proposing. This model is used to predict the shape of molecules, and the key idea of the model is that molecules will assume a shape that allows electron groups around a central atom to get as far apart from each other as possible due to electron-electron negative charge repulsion. Negative charge and negative charge repels. We've explored that idea. So electron groups will assume a shape that allows them to maximize their distance apart from each other. These electron groups can either be single bonds or multiple bonds, as in double or triple bonds, or we can consider an electron group to be a lone pair. So let's turn our attention to 3 examples where we can explore how the VSEPR model would predict the shape of each of these molecules. The first molecule we're going to look at is the molecule carbon dioxide. And if you take a minute and use the 4-step process that we discussed previously about how to draw the Lewis dot structure for carbon dioxide, you're going to come up with this drawing. And our focus is now, what shape should the carbon dioxide molecule have? Now, when we look at the molecule, I can see that carbon is the central atom, and I see that there are 2 double bonds between carbon and each one of the oxygen atoms. But for VSEPR purposes, these double bonds count as one single fat electron group. So just sort of highlighting those double bonds as if they were extra large balloons, I see that there are 2 electron groups around the central carbon atom. And what do 2 groups do that want to get as far apart from each other as possible? What they do is assume a linear shape that maximizes their distance apart from each other. In other words, they will move 180 degrees apart. So as a result, when we look at the shape of carbon dioxide, we see that it is in fact a linear molecule, right? So each of the sticks that I'm showing here is representing what is in reality a double covalent bond. And unfortunately, I'm not able to hold that in place well, but I'm showing you here, I recognize that there is a double covalent bond between carbon and oxygen. So the black ball, central ball, is carbon, and the 2 terminal red balls are oxygen. They are doubly bonded, but for the purposes of VSEPR, those double bonds count as just one single electron group. So we have a 180-degree separation between those electron groups as they push as far apart from each other as possible, and the overall shape that the molecule assumes is a linear shape because the electron groups have a linear arrangement. So a linear geometry or shape for the electron groups, which maximizes their distance apart from each other, and carbon dioxide is in fact a linear molecule, and we have drawn its shape quite well as we examine it closer. It is a linear shape. Let's take a look now at our second example. This example comes from organic chemistry. The molecule is formaldehyde with the formula CH2O. If we draw the Lewis dot structure for formaldehyde, we come up with this drawing. And let's just stop and see here what sort of shape we would predict the electrons are doing around the central carbon atom. Again, multiple bonds count as one single electron group. So as I count the electron groups around the carbon atom, I am counting 3 electron groups. And what do 3 electron groups do to get as far apart from each other as possible? And the answer is they assume what we call a trigonal planar shape. So looking at the formaldehyde molecule with the yellow sticks representing the electron groups, I see that these 3 electron groups, in order to maximize their distance apart, are assuming a trigonal planar shape with bond angles of 120 degrees. So I am going to redraw my formaldehyde molecule to show the shape that the electron groups are assuming. They are moving 120 degrees apart from each other. We call that the bond angle that is found in the molecule. So bond angles of 120 degrees separating these electron groups from each other, and the name that we give to this electron group shape is trigonal planar. Trigonal planar. Now the planar is referring to the fact that the molecule is a flat molecule. All of the atoms lie in a plane, and you can pass a piece of paper through them and bisect all of the atoms because it is a flat molecule. The trigonal, of course, is coming from the fact that there are 3 electron groups around the central atom. So again, if you identify that situation, 3 electron groups around a central atom, you know those electrons are maximizing their distance apart by assuming a trigonal planar shape. The last example that I would like to look at is the molecule methane. Again, it falls in the organic compound category. If we draw the Lewis dot structure for methane, we see that carbon is singularly bonded to 4 hydrogens, but it looks like from our drawing that methane, it looks like methane is a flat molecule, and these bond angles look like they are 90 degrees or at right angles. But in fact, methane is not a flat molecule. In order for those electron groups to maximize their distance apart, methane assumes what we call a tetrahedral shape. So we're focusing on these 4 electron groups and how to maximize the distance apart from these 4 groups. You can see that the bond angle is in fact bigger than 90 degrees. It has a value of 109.5 degrees. So if I was trying to draw the actual electron geometry around the methane, I would have to show that these 4 electron groups are assuming what we call a tetrahedral geometry. A tetrahedral geometry. And the way I represent that is by trying my best to capture that 3-dimensional shape of the molecule. So the line here means that the carbon and hydrogen are in the same plane. A dotted line means that this hydrogen is pushing back behind the board. And these wedges mean that the remaining hydrogens are projecting out in front of the board. So here is my drawing of the methane molecule trying to capture this tetrahedral geometry of the 4 electron groups around the central atom. And perhaps I can make this a little more dotted, right? Make it pop a little more. This tetrahedral geometry. Again, this carbon-hydrogen in the same plane. The 2 wedges refer to the hydrogen atoms that are pushing forward out of the plane. And then this dashed line referring to the hydrogen that is behind the plane formed by the bond between carbon and hydrogen here. So tetrahedral geometry. And the last thing I want to indicate in the drawing is that the bond angle, whenever the electrons are assuming a tetrahedral shape, the bond angle for the electron groups would be 109.5 degrees. And you are responsible for knowing that if it's a linear geometry of electron groups, the bond angle is 180 degrees. That if the electron groups are trigonal planar, because there are 3 of them, the bond angles are 120 degrees. And if the electron groups are present in a set of 4, the bond angle that maximizes their distance apart from each other is 109.5 degrees.